Hi everyone, this is Annie. Just checking everyone's auto, maybe specifically our audio. Eric and Zenlong, just to see that I could hear you guys.
Hi, this is Eric, and I just unmuted, so hopefully you can hear me.
Yep, Eric, crystal clear. How are you?
Doing great. How are you doing?
Great, great. And Zenlong, do I have your audio? Let's see. I can't hear you if you're talking now. All right. Let's see. Zenlong, oh, Faye is there. Let's see.
Hello, this is General Lee.
Hey, Zhenlong. I was just checking your audio. I can hear you now.
Yeah. Okay, I think I'm good now. You are Annie, right?
Yes. Good, good,
Okay.
great. All right, and it looks like Faye, do we have your audio as well? Not yet.
Hey Annie, it's Erin.
Hi, Erin. And it looks like we've also got Christine. Hey, Christine. Dan, welcome. And we also have Robert and Alexander. Welcome to the call.
Thank you. Looking forward to this.
Let's see. Hi, Faye. Do we have your audio?
Yeah, I can hear you. Could you hear me?
You bet. Loud and clear.
Okay,
and we've got Young Yao is coming on now. Let's see, Young Yao, do we have your audio? You're muted if you're trying to chat. Hi, great. All right, well, it's 1 after 11, so I say we go ahead and get started. Zhenlong, I'm going to just mute you since I think I'm getting a little feedback. And welcome everyone to the call to this testbed report out. Today we have 3 projects that are going to talk. Unfortunately, Louis McGibney, who is one of the co-Is on one of our projects, had a last-minute commitment and couldn't make the call. So he's kind of taking the lead on the project, but Young Yao, his co-I, is going to give a kind of a short project overview and not a full report out today. So I was thinking we could just start off with that since it'll be a fairly short description, and then we can just start at the top and pass it over to Eric, and then Faye and Zhenlong could finish it up today. So Young Yao, do you want the control of the screen, or do you want to just chat?
Yeah, maybe it's easier if I can share my screen.
You bet. I will pass that over to you now. Okay, you should be able to share.
All right, cool.
All right, and we can see your screen?
Yep.
Okay.
So, okay. My name is Yong Yao. I'm a PhD student at George Mason. And for the past few months, I have been working with Louis from JPL on this ESKG project, and which is short for an automatic approach to building Earth science knowledge graph to improve data discovery. So as you can see from the title, the goal of this project is to is trying to develop a method to generate Earth science knowledge graph, which can generate rich graph data for query and analysis. So basically, we have set up a code repository on GitHub, as you can see here, and also a mailing list through Google Groups. So basically, so far, what this code can do is that we can so I think Louis has set up a tutorial here. Cool. So basically, what we can do right now is that we can convert, for example, a data set landing page on one of the data centers like PODAC into a structured triples here. So for example, the original data is here, the Aquarius project landing page, basically some plain text, and then we can convert this web page into some structured information, as you can see here. So first of all, the number here means the confidence that we have that this triples is meaningful. For example, the first one, the Aquarius launched, at some time. So basically, this makes sense to me. But as you know, all of the automatic approach has some kind of noise. So right now we are trying to kind of filter out this noise. So this is what we have got so far, and I just came up with a few key points here that I can talk through. So basically, the key technology that we are using in this ESKG project is OpenIE, which is a natural language processing tool that we use to perform unsupervised relation extraction from plain text. And the other one is called ANI23. Basically, it provides a basic crawler and also a format converter, which can convert the HTML file into a structured like JSON file or XML. And the data we are using here, right now we are focusing on the PODAC web pages, just as I show you the dataset landing page. And the result data can be stored into the ESIP semantic portal as well as the community ontology repository. And in addition to that, we are kind of collaborating with a guy from Justin Goldstein from NOAA. Someday he just shoot us an email that he's very interested in this project and ask if we can do some work together. So we're nearly ready to extend the ESKG to the NOAA data as well. And next, we are going to set up a website for this project and also aiming for 1.0 software release once we have complete the initial workflow. I think that's all of the progress I'm aware of. I think Luis will talk more about this in a call like in near future.
Mm-hmm. Great, Yang Yao. That was a fantastic overview. Does anyone have any questions about the project for Yang Yao? Hi, Ken. I see you unmuted. Do you have a question?
Yeah, actually, I came in just a few minutes late, but I gather from what I was hearing that what you're doing is searching for the data information on the web pages, not necessarily in the repository of metadata. Is that right?
Yeah, so what we are trying to do is to convert the plain text on the web page into some structured information. At this point, we are not doing anything with the metadata because metadata itself is already structured.
Right, but I mean, if the goal is to get the best information, potentially the metadata would be that best source, I would think, right?
Yeah, I was talking with Luis just the other day. Maybe we can, convert the metadata into some kind of triples and then combine these triples with the information from web pages to to build a more comprehensive graph.
Yeah, because some of the we've dabbled with this a little bit in the past, and one thing that could be an offshoot of this potentially, if you were using the metadata repository directly, is also helping to identify where there's holes in the metadata about the data sets.
Yeah, that's a good point.
Yeah, okay, thanks.
Thanks, Ken, for that comment. Yeah, Yang Yao, I mean, it seems that there's often associated when a researcher might enter or add a data set somewhere that they provide some of this unstructured text as a descriptor, and then they have their structured metadata, but without knowing, they're providing a lot of rich information and that kind of unstructured text about the data set. So it would be useful to have that information as well as the structured text and the metadata. So, I mean, at least that's kind of what I'm getting from this in part. And you can correct me if I'm wrong there. All right, so let's move ahead unless anyone has other questions for Young Yao. All right, great, thanks. So Eric, are you ready to go next? Can I make you the presenter?
Yes, I'm ready to go.
Screen.
Okay, all right. Eric, you should be able to present now.
Will do. So our project is literally looks at the cloud and works through the cloud and does some masking of clouds. But specifically, we look at snow cover. So this map shows the snow cover frequency, or the amount of times within the Austral winter, the South American winter, that snow appeared. We use these. This is a static map, basically looking at everything throughout the winter. But if you really want to look at what happens with snowpack changes on a day-to-day basis. MODIS data, specifically the MODIS 10 A1 data set, provides daily coverage of changes in snowpack. And as you can see, it within this focused region in northern central Chile, snow changes quite a bit throughout the Austral winter. So with that, this kind of stems from some research that I did while I was working in northern central Chile, specifically looking at stream flow and predicting stream flow into upper elevation reservoirs. And in these upper elevations, access is incredibly limited. It's not like the North American mountains where there's access is challenging, but there's still some data. In these areas, there really is no data, but you still have the same water issues. You still are looking for water. You're still trying to figure out how much water will be coming into a reservoir for planting. So basically, with just going with when you don't have data, when you don't have precipitation data, or you don't have measurements on the ground, we developed a simple conceptual model that looks at changes in snow cover frequency, or changes in snow cover at a monthly time step. And we have measurements of stream flow from previous months coming into an upper elevation reservoir. And with that, we use those two in combination to project stream flow with 1 month anticipation. This is kind of the simple conceptual model. And basically, it's a snow melt runoff model, fairly common in hydrology, but typically they don't use remote sensing data. They use a temperature-based approach. We use the snow cover frequency product. Again, this uses with 1 month out, predicts stream flow using a 4-parameter model. Q meaning stream flow, that's the near term, within the last 2 months. The Q long is the long-term stream flow over the year, which represents long-term conditions. If you're in a drought, the long-term stream flow is going to be low as compared to high. The snow cover frequency, SCF, is again, it's represented. This is the primary input into the model. This comes from the MODIS snow cover data. And it's a simple 4-parameter model. This is published, I guess it was published last year. And the model works quite well. Again, with 1 month anticipation, you can see the model, the measured stream flow in the blue line matches quite well to the modeled result in red. Catches both the low years, the low drought years, going from around 2009. My mouse disappeared. Going from around 2009 through 2015, and then normal years on either side. This initial model was done in a fairly rigorous approach using MATLAB, using Monte Carlo simulations. I then tested it to see, trying to simplify it for users, to take it out of a research mode and into an applied mode, especially for folks who are making decisions who might not be experienced with using Monte Carlo simulations. So basically, I was able to put this into a Google Sheet format, just a simple online spreadsheet, and the model works just fine. The trick to doing that is you still have to calculate the snow cover frequency each month. That means downloading, around 31 images, reprojecting the images, reprocessing it. It takes about a day and a half to do that, which might not seem, in a place with deep human resources, that's not as big as problematic. And Chile, things run a little leaner. So we really wanted to, and finding the time, a day and a half to process images every month was quite challenging. So what our goal was to take the next step and move this into a more automated format for the processing. And to do that, we use the Google Earth Engine. So basically, if you're not familiar with Google Earth Engine, Google has made an online product. It's all entirely web or cloud-based and allows you to access almost the entire NASA data set. So specifically, and you do it all through just simply JavaScript code. So here's, this line of code basically says for all the MODIS data, grab the entire image collection off of the server. So instead of having to download 15 to 16 years worth of data, or in this case, it looks like this is just for the month of December 2016, it does everything in the cloud. There's no downloading, there's no reprojecting, everything is done in the cloud. From there, we have different algorithms that can calculate snow cover frequency, as well as ones that have a cloud mask. So basically what it's saying is if it's cloudy, we have certain rules in place to compensate for cloud cover. Once we have these processed, we want to move these calculations into the spreadsheet format to automate I should say to streamline the ability to make streamflow projections. Streamline the streamflow predictions. So basically, the three goals of our ESIP Testbed project was to develop the cloud-based tools to calculating the snow cover frequency, and we want to use that information to drive this snow melt model that we've developed previously. But we didn't just want to develop it; we also wanted to provide these tools to the users. So we're working with water resource managers. We'll provide both the tools and the tutorials to use them, and then we want to get their feedback. What works, what doesn't work. And we're doing this in 3 different watersheds, 3 distinct areas. The Rio Elqui, which was the example I showed you previously, which is in northern central Chile, the John Day River, which is in central Oregon, and the Rio Aragon, which is in the Spanish Pyrenees in the north. These are all snow melt dominated watersheds with just different climate signals, but for the most part, they're winter wet, meaning that the bulk of their precipitation comes in the winter and comes as snow. So we set out to do this. We went and developed a series of programs or scripts, I guess, in the Google Earth Engine. And basically what it allows you to do is calculate snow cover frequency for the entire globe. So here's just a screen capture. So what this is saying is it calculated snow cover frequency for the entire MODIS record, 2000 to present, in just under 5 minutes. I mean, take a step to think about that. In under 5 minutes, we calculated, global coverage of snow cover, and we didn't have to download 1 bit of data. We didn't have to put anything on our servers, reproject, but this calculates that kind of base data set. Incredibly valuable if you work in snow and snow hydrology. So once you have this set up, this initial calculation globally, you can then go in and look at a focused watershed. So with this, within the GUI, within the user interface, you can choose which watershed you're looking at. This is the La Laguna or Rio Elqui watershed in northern central Chile, and it performs metrics or calculates metrics using the snow cover frequency. So this calculates, your mean elevation, your area, looks at snow cover frequency with the cloud mask and without the cloud mask. I should say with the cloud mask. And then it also plots it out. So this is from 2002 to 2016. You can see the calculations. Again, this is done entirely in the cloud. Similarly, for the Aragon watershed in northern Spain, you see a similar type pattern. So this, again, all done in the cloud, no downloading data, but it gives you all of your information. The charts that are embedded in the map are also, you can look at them in a little greater detail. These are all interactive, again, online. It allows you to download the raw data or simply the image as well. Again, this is just a more in-depth look at the Aragon River in northern Spain, the statistics, and then the plot that accompanies it. Our next step was to get these data, because you can download these data, these at a monthly time step, and transition it into the model itself. So here's the general framework of the model within Google Sheets. And to optimize the model, I simply used the solver function, which comes right with as an add-on within Google Sheets. So instead of doing a more complicated Monte Carlo simulation, ran the solver function. So basically this is saying, the objective E7, we want to maximize that and change the parameters, which are B1 through B4, that simple parameter model. And it's going to give us predicted stream flow, which is the E column, using columns F through I. So again, we're predicting stream flow in column E using columns F through I. And you can see in the pink highlighted box, it gives us an efficiency rating, a Nash-Sutcliffe efficiency rating of 0.87 out of 1. That's quite good for a stream flow model. 0.87 is very solid. And this is again using all the data from the Google Earth Engine. Previously the model worked, but we had to download, reproject, and it actually didn't work quite this good. I think it was the published paper was 0.84. So this actually gives us a little better result. We tested this model. We're in the process of testing this model. I also did it in the Rio Aragon using simply the same framework. It didn't perform quite as well, but again, this is kind of off the shelf. Have not customized it for the Rio Aragon. There's a couple things I want to change, but obviously we're on the right path. Similarly for the John Day, we're around the same level of model skill. So our next steps are again, refine the model for the John Day and the Rio Aragon, and then move on to providing these tools and tutorials to the water resource managers, because two of the watersheds are in Spanish-speaking countries. The tools, or especially the tutorials, will be provided in Spanish as well. We're partnering with Ignacio Lopez in Spain, and he'll be able to translate these tutorials. And then we also want to just give these to the users, have them simply provide feedback, what's working, what isn't working. So for iteration 2.0, we can really not just look at it as a researcher, but you look at it, really connecting the user to the data and the tools. And that is where we're at.
Great, thanks, Eric. Well, for those that don't know my background, I was a snow hydrology focused PhD, and so I am particularly excited about this project, and I'm going to try to refrain from asking lots and lots of questions and kind of let others on the phone pipe up. So does anyone have any questions for Eric at this point?
Well, I guess I'm the only other one on the call here, but but I'll jump in. From a resource perspective, Eric, I'm curious about your use of the Google Earth Engine, which is really interesting. and I've just started to dabble with some other applications that are being supported that way as well. What I don't know that I wanted to ask you was, what's the long-term sustainability of using that? Is that a cost item? Does that eventually, incur cost to use that? What's the long-term status of that, to host this type of application?
Right. So that is the $1,000,000 question. Actually, hopefully it won't be $1,000,000 question, but that's an excellent point, and one that we debated, bouncing around. Google, they don't know exactly what the long-term goal is for Google Earth Engine. As of now, they want people to develop tools on it, try to break it, see what works, see does it work, see what doesn't work, and they provide a great platform to do that. I think it also provides, whether Google Earth Engine is what we're using in 10 years from now remains to be seen. But I do know that right now it works very well. And I also think Google Earth Engine will drive competitors, whether those competitors be government agencies, not competitors, but will stimulate innovation potentially within government agencies or other private companies to move forward. I do know that the heavy lifting of so many of remote sensing projects is downloading, reprojecting data, getting it in line. It's this excuse me, this bypasses all of that, and the cost savings on that end, just in terms of human resources, are great. It doesn't cost any money to use the package. If you want to upload, you have data limits, but as of now, we haven't even come close to reaching them.
Okay, so you're using a free tier now? Is that
correct?
Okay, so do they have a paid subscription level that could be used?
So that's only if you're uploading your own data.
Okay.
So if you upload your own data I can't even remember what it is, but I think it's several, maybe 100 gigabytes or something like that.
Okay.
So if you're looking at global coverage, you'll hit that pretty quick. If you're looking at a more focused project, I don't think 100 gigabytes is pretty manageable.
Okay, thanks.
Thanks, Ken. Any other questions for Eric? Eric, I have one. So you're saying the NASA archive is available through Google Earth Engine. Do you know if any other of the large data providers have made that same commitment?
No, and I didn't want to open up my I closed my web browser just to try to speed things, make sure nothing bogged down. But I can send you a link of all the data sets that are available.
Okay, great. Yeah, I was just saying if any of the NOAA folks on the phone knew if any of the kind of the NOAA archive was similarly available through Google Earth Engine. And I was going to ask just if there were any particular data challenges related to this. I mean, is it pretty seamless in terms of accessing those NASA data within that space?
Yeah, I mean, you literally, this is the call to get all the MODIS 10 this, can you see, is it
Yeah,
visible?
I can see that. So it's basically just image collection.
Basic setup. That is the call to get all of the data.
Okay.
I mean, and then you see below you have to filter in by band. So
Yeah.
200 is cloud, 20. One of these is cloud, and one of them is no snow. But
Okay.
it's pretty slick.
Yeah.
It's straightforward.
Okay, great.
These are the data that are available.
Oh, okay.
Let me minimize my. So you have.
Mm-hmm.
So there, yeah. So you have the GFS, Global Forecast System, as well, and the INSEP.
Okay. Great. Well, before we move on, any last questions for Eric? Great. Thanks, Eric. Looks like you guys are moving right along. So Faye, Should I pass the presenter to you?
Don't know where give a presentation.
Oh, hold on. Let me
Yeah.
mute. I'm going to go ahead and mute Eric. Say that again, Faye.
Don't know where give a
Oh,
presentation.
Zhenlong. Okay. Let's see. Zhenlong.
Could you switch it to me?
Presenter. Okay. All right, Zhenlong, you should be able to present. I'm getting an echo, so I'm going to mute myself here. Well, let me wait for Zhenlong too. Zhenlong, you should be able to share your screen now. And Zhenlong, you are on mute in case you're trying to talk. Oh, we can see it now. And Zhenlong, in case you are trying to speak, you are still muted. Oh, looks like you're not muted.
Okay.
Yep, we can hear you now.
Okay, that's good. Okay. Yeah, no one asked a question and didn't hear any response yet. I didn't see that I'm muted on my computer. Okay. Okay, that's good. Can you see my screen now?
Yes, we can.
Okay, that's good. So here should be, let's do this. How about now? Can you see which screen?
We can see your presenter mode, but we can see that slide just fine. So we can see
Okay.
your
Okay,
slide.
you see that, right?
Mm-hmm.
So this project is working with Faye now, and the title is Prototyping a Cloud-based High-Performance Visual Web Portal for the parallel analytics of big time data. So here we are focusing on parallel and also analytics, and also big time data. That's the problem we want to address here. And first, I'm from University of South Carolina. I'm assistant professor here, and my research is mostly working on big data, HPC, and also analytics. Next slide. Let me something else. Wait, my computer is dead. So first, today I want to give about like 5 or 6 minutes presentation, like to show, to just give an introduction of what we are doing, and also I'm going to give a live demo to show what we already have now. And so the motivation, what we want to do this, the reason is that there are a lot of climate data there, and they are generated from different sources like modeling and satellite observations, sensors. So all this data, they are large, and we need to find an efficient way to process them. And for example, here, for the IPCC report, for the recent report, it produced 10 petabyte climate data. And that's a good example. And also in NASA, they are archiving a lot of climate data. For example, the mirror is one, it's a set of products. It's about real analysis data. So there are a lot of data there. It's very important for us to efficiently analyze this data, and so we can quickly identify the knowledge or extract the information from there. And with traditional approaches, like using a desktop, and it's hard to do this, like we are drinking like this diagram showing here, drinking water from a fire hose. So that's a challenge. And so based on this challenge, we are asking a question. So is there a way that we can just do a simple search? For example, as here, you can see there a SQL query here. Can we just do a simple search to answer some very typical climate analysis of questions? So one example here is that, for example, the mirrored land data is from NASA, and it's available from 1979 to present. And the temporal resolution is this one, is 2 or 3 degrees, and longitude is half degree. And the data size is 1.8 terabytes now, just only for one data set here. So the question, if we want to ask what is global annual mean land surface temperature for the afternoon hours during this time period from 1979 to 2015, how can we answer this question? And one way to do this, and for now, we need to you want to download data, okay, if you can do that, and you can search some tools and download the tool, install that on your computer, and you can write your own program, like using NCO, some other NetDev operators, like scripting to do that. So here, what we want to do is that we want to develop a tool to do it very simple. We want to ask the user to just write a simple query like this. Select year and some spatial temporal operation here and some spatial temporal conditions put it here, and then you can get a result. The result can be directly visualized on the web portal, and all this query here, including the result, can be stored in the system, so it can be queried by someone else. And if someone has similar questions, maybe you just need to change these numbers or change this operation here, and they can, based on that, to do more analysis. So that's what we want to do here. And here is the architecture that we proposed in that proposal. So here, because we want to first based on cloud platform here, and also we want to handle the big time data. So one thing we are doing here is that we store all this data in the Hadoop distributed file system, which is a distributed file system, and we put it there, and we support two types of data. One type is array-based data, which is like for most output, they are array-based data. And also for the satellite images, they are array-based data, like HDF or NetDev other images. And also we want to support the record-based data, which is like weather stations. And for the global weather station, they're the billing of record there. We want to also include this. And then we load all this into the HDFS, Hadoop file system, and then we build index, and finally, once we have this data managed, we build a hybrid parallel query engine. And that engine we want to integrate Hive, which is Apache Hive. We can develop the UDF to do the spatial query, spatial analysis, and also we want to utilize the Impala here, which is in-memory compute cluster, which we can get a response within several seconds. And then we have this part here is a query middleware. Like we try to build this kind of component so we can receive the user queries, and then based on the queries, we can select corresponding query engine. For example, if a query is querying, like for example, that a mirror data, we want to use Hive. If we are querying record-based data, we can use Impala to get a very faster performance. And this, at the same time, we are building a multi-level caching mechanism, which means all these queries can be cached at different spatial and temporal resolutions. For example, we can cache the hourly data into the daily or into monthly. So that's one cache. We can also cache data at different spatial units, like in a state or in a county. So that can all be cached. That's our final goal here. And finally, based on this, we have this query interface, which is a web portal. So this one, user can build a query and finally submit the query. The query is going to be running in parallel on our platform, and the result is going to be parsed back to the platform and directly visualized. And the visualization is specified by the user. So I'm going to demo that so you can have a sense of how it works. And this here is a very simple query here. We are selecting this average, spatial average, and temporal average, and here, and specify some visualization types. So you can see that we can finally make show a map on this globe, 3D globe. So this architecture. So these are very lot of work that need to be done, but we are basing, when we develop this architecture, we are basing our previous work. So we have done two types of work here. First, we developed a spatial temporal index before, and so this index can be used to store the HDFS data directly into HDFS file system. And also we build a query analytics platform, not platform, it's just a method or engine before. So this one can be integrated here to do the query. But in this architecture, we extend that to include like this hybrid engine, wanting to integrate the Impala. Also, we have integrated these other data sources, not only array-based data. And also we put multiple level query here, multi-level caching here. And finally, we the key here is to build this user interface so you can easily submit the query and retry the results. So all this can be documented in the system. And this is quickly some images that, let's see here. Okay, this is the interface for the prototype right now. And I'm going to show you a live demo now. If you can see my screen, and so this is a user interface for now, and it's only a prototype. And on the left side, there are some queries that for each query you can name it, give it name. All these queries that I've done before, just using as examples. For example, the first one is anomaly analysis for the winter, and then when you scroll down, you can see this is a query here. They are all based on Hive syntax, but we extend that to include some other, like include some other feature. For example, you can put visualize as here to support visualization, and also we develop different spatial temporal analysis function like average based on time, and also you can average based on the spatial region. And here you can see there's calculated standard deviation for the time series data. So all these are user-defined functions that can be extended here. So this is the query. Once you submit the query, you can get a result direct like this. So the result first is a table, and you can download that as CSV. And for this result, we can also visualize that as animation here because the user specified it. So if you click animation here, and it will show up directly on this 3D globe here. So you can also click one year, for example. You look at this temperature anomalies, and that's for the animation. So this is one example to show you how you can conduct anomaly analysis based on the 37-year or 36-year data from 1979 to 2016. Okay, when you look at this left side, there is also several other columns like the time here and select the engine. So the time on our cluster now it runs about 326 seconds. So our cluster consists of 13 servers, 12 computing nodes actually there only. We select the engine is Hive here, and there are some other query. For example, to show you the query multiple variables here. And okay, query multiple variables. Still, the result is going to show here. And let's look at the query first. This one just want to show you how we can query different variables from this data set. From this data set here is mirror here. Okay, I forgot to mention it's about query the mirror here, not a mirror. And we are querying several variables here. And these variables are grouped based on the time, like the summer time. And finally, once we get all these variables, and I visualize them as time series, scatter plots because they are multiple variable, and we can do animation. We can also do parallel coordinates, show them a temporal, heat map, and scatter plot. So all this visualization can just click here. There's a time series for different variables. You can click that. And scatter plot, this is for, you can select two variables here to directly see the correlation between these two variables, any two variables. And scatter matrix, which is to show directly multiple variable correlations in one diagram. And you can quickly identify which two variables has some relationships. And parallel coordinates, there are another way to look at this multiple dimension here. It's all drawn in real time, and you get this data. You can just show that here. And heat map here. Also, we can draw the temporal to show the temporal trend with a heat map. So this is the day of each. Like, oh, this is the day. For example, 2015, July 1st, July 2nd, and this is the hour. So this map is going to be produced automatically based on your time data. For example, if you have a monthly data, it will be different, but it still will be automatically show this map in a different format. And because this is time series data, we can show it in animation. You can also animate the data, for example, like this. Just need to click the start, and you can change the state of this animation. And you can see the animation here. You can also change the projection of this globe here. So it needs some time to download the data. That's why you see it's flicking. Once it's downloaded the first time, it will be very fast to see this temperature change here. So this animation is only showing one variable, because here we can. The variable is, let me take a look. It's showing this render here. The render here is showing this TSU variable. When you look at this result, you will see this variable actually. This column is showing this image names for each of these frame here. And so that's the basic query here, and also how we can visualize this data. Now the data that we included 3 NAPA data sets, all for mirror, and there are two-dimensional data and 1 three-dimensional data. So the total data size is about 3 terabytes. So when you look at this query, it takes about 5 minutes. So actually, we are actually querying almost 3 terabyte data, and some other queries takes a shorter time, and that's based on how many data that you actually have involved. You are involving in that query. And for each query, you can also put some comments here, and this can be saved. And also, you can put your email address when you submit the query, for example, and I can, like, using 2, 3 here and click submit. It will do the query, and once finished, you will get an email notification about this result here. And also, you can search something like, I want to search a temperature, and all these queries that has temperature keywords in that will be found out. So this sounds like it's a knowledge base. So you can, once you do this query, you have this query, you have this process to solve this problem. You also have all these results documented. You also have that visualization maps that are there. So others can, based on this query, to build new queries, can be saved and can be shared, and everything just can be done on this web portal. That's pretty much what we want to do here, and so that's a demo. So finally, I think we are making good progress towards finishing the project. So for the next, we want to develop a Drupal-based website and to integrate this application, and also for information dissemination purpose. And the user can share the queries, some feature query, for example, and they can collaborate and discuss different, can share their query code in the web page, and also they can have discussion on there and to solve a specific problem, for example. And also we need to do the system test and evaluation. Finally, we want to report the project at the ESIP meeting in this research and art section. And that's it. Thank you.
Great. Thanks, Zhenlan. You've clearly a lot has gone into this. So I'll open it up again to questions from anyone.
This is a question from Christy.
Hi, Christy.
Hi.
Oh.
So I see the tool is available. I didn't play with it while you were demoing because that wouldn't be nice.
Yeah.
But I see that folks can access it.
Yeah, you can access that. But it's not stable yet. It's not stable yet.
Yeah.
Yeah. You can access. Yeah.
Are you interested in? You had mentioned folks sharing their analyses and different, like what you're showing right now on the screen, different queries that they run. And I know that you're presenting at Research as Art. That's great too.
Yeah.
Do you invite folks to work with the tool and and kind of tell some of the climate trends they're seeing or some of the analyses they're doing? Or should we not play with it for a while until research as art?
I think for now, because it's not very stable, so we can use that, you can access that now, but maybe there's sometimes the server may be down and there may be some errors. Yes, I think definitely. Finally, we are very happy. We are going to invite the people that in that field to play with this and to use that. So yeah, I think that's our goal, to make this tool and to be used by others, not in the lab. So yeah, definitely. But if anyone wants to use that to play that now, that's okay, but the problem is that we don't have much documentation right now on this website, as you can see. So and how to build these queries, and also what kind of data are there, and the documentation not that complete. But when you click data, you can see some variables here, but they're only very basic.
And because you guys are just halfway through at this point. I think this is the midpoint report out, right?
Yeah.
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 And
also,
I think about when we're exploring these data sets and finding trends and looking at things, how you can reuse the knowledge. One person's subject matter expertise can inform another person's subject matter expertise. So, thank you.
Thank you.
Thanks, Christine. Any other questions?
Yeah, this is Ken at UH again. So I'm really interested in all your tools and capabilities you're making available on top of this data. That's is very interesting. I'm a little questioning, I guess, the back end, trying to get the data into the system. From what you were describing there, appears to be somewhat of a task, I think. Plus, I assume this is hosted on your private cluster, right? So what's your long-term plan of how this might be available for other users to use this for other data sets?
Yes, I think currently, because it's only a prototype, and so it's like proof of concept. And in the long term, probably I'm not going to host in my private cluster for all the times. I'm looking for some other funding support, or some agency. Maybe they want to can make this more mature and then get host there to put more data there, and also to try to broadcast or disseminate this tool more widely. But for now, we just want to prove that, to demo that it's working and it can be useful to solve some problems.
Okay.
Yeah.
Thanks.
Yeah. Thank you.
That's a great answer, Zhenlong. I think it also speaks to kind of a good example of an ESIP Testbed project where we can provide funding at this level to help you develop this proof of concept and present it, and it gives you that initial seed. So that's really great to hear, and I guess I could apply that to all of these projects. And it seems like everyone has put a lot of effort in and has been able to really utilize this initial funding. So any further questions for Zhenlong? All right. Well, seeing none, I'd just like to thank everyone that presented. Eric and Young Yao and Zhenlong, I really appreciate it, and we'll look forward. I believe everyone on the call today will be at the ESIP summer meeting, and I've encouraged everyone to present either at Research is Art or within a session. So if anyone has any follow-up questions, please feel free to seek these folks out this July in Indiana. And if anyone doesn't have any final comments, I'll just say thank you to everyone that attended the call. And the call has been recorded. So I will post that link soon. So thanks, everyone. Have a great afternoon.
Thank you, Andy.
Thank you.
Thanks, guys.